Good morning, grade 11s. Today we're going to look at the strength of acids and bases. So you might have heard me talk about weak acids and strong acids, that weak acids are ones that we can ingest and strong acids are one that does a lot of damage. Sometimes the term strong and weak acids is strictly in connection to the concentration, because there are some acids that are classified as weak acids that do a phenomenal amount of damage if it's spilt on your skin, to the point where getting from here at school to the hospital in Fairview, you would probably lose the majority of the area where you spilt it. So, but yet it's still classified as a weak acid. So we're going to go back through properties of acids and bases, and we're going to talk about what makes them a strong acid, what makes them a strong base, what makes them a weak acid, and what makes them a weak base. So this is lesson 6.5, strengths of acids and bases. When we go through and we talk about the empirical properties for acids and bases, remember, empirical are the physical, tangible things. What can we see? What can we smell? What can we taste? What can we hear? What can we feel about acids and bases? And so what you might remember is that acids taste sour, whereas bases will taste bitter. You might remember that litmus paper that's blue will turn red, and here red litmus paper will turn blue. You know that it's a pH of less than 7, whereas the pH here is greater than 7. Remember, we're talking about the pH scale. I apologize that you can't see this very well. We also stated that acids will react with metals to produce a hydrogen gas. We know that it will react with carbonates to produce carbon dioxide gas. So whenever we're looking at gases, we're going to be looking for bubbles to appear. The other piece of information over here is that while acids will burn the area that it spills on, and by area, I'm specifically talking about getting it on your skin. If you were to get a base on your skin, it would feel slippery. And what's happening is that the hydroxide is reacting with the fat cells in your skin to turn it into soap. And then the big one is that acids will neutralize a base, whereas bases will neutralize an acid. So those are empirical things. Those are things that we can taste, things that we can see, things that we can hear, things that we can feel. So those are empirical properties. This piece here, do all acids and bases have the same properties and to the same degree? This is an in-class lab, and unfortunately we're not going to have that option. What I am going to do is I'm going to look for an online lab that you can do through a simulation. And so this particular one is looking at different properties of acids and going through the design process, or what we would call the procedure, and what would be noticed to be the difference. We'll come back to this. I'm going to leave these two off the table for now, and we'll come back to it either when we're back in person or when we can find an online lab. This part here, strong and weak acids. We're going to focus on acids in one stream and then bases in another stream. I really do apologize, but this is harder to see. Okay, so the concept of a strong and weak acid is developed to describe the difference in the properties. So the difference in the characteristics such as producing hydrogen gas, or the characteristics of the pH scale. A weak acid is going to hang out around 4 and 5, and a strong acid is going to hang out around a pH of 1 to 3. There are 6 strong acids that we deal with. Some of you made yourselves familiar with the acid table when you were learning how to name acids, which is fine. But this is page 8 to 9 of the table, and what you can see, it says relative strength of acids and bases. And these 6, 1, 2, 3, 4, 5, and 6, are what we call the 6 strongest acids. And so when we write them down in our notes, we have perchloric, HClO4, perchloric acid, we have hydroiodic acid, we have hydrobromic acid, we have hydrochloric acid, we have sulfuric acid, and we have nitric acid. You are required to know these 6 acids by being able to know how to write from the word perchloric acid that you would get HClO4, or from HBr and being able to know that it is hydrobromic acid. Not relying on page 8 to 9 to tell you that. These are 6 very common ones, or they are the 6 strongest ones, and so you just need to commit these to memory. When we use the modified Arrhenius theory, remember we're looking at a hydronium ion and a hydroxide ion as opposed to a hydrogen ion in exchange. High conductivity, a high rate of reaction with metals and carbonates, and a relatively low pH. This is the definition of a strong acid. They have high conductivity, means simply that they conduct electricity very well, remembering that conductivity means the solution must be an electrolyte. High rate of reaction, meaning that when I write the reaction for nitric acid and water, that it's going to give me an H3O ion and an NO3 ion. And there's no fooling around. It's going to go. That reaction is going to happen. These empirical properties say that the ions are present, which consists with the idea that strong actions react completely. They react completely with water to form hydronium ions. Okay? 100%. Wow, greater than 99, but 100%. They react. The difference using modified Arrhenius theory, when we're looking at low conductivity, low rates of reaction with active metals and carbonates, and a relatively high pH, we're looking at not that we're looking at a base, but that we're looking at a weak acid. This is a little misleading where it says a relatively high pH. This means like 4 to 6, not anything above 7, but in the higher end of less than 7. When we see that it has low conductivity, so we're not getting much electricity moving through the solution, we're seeing that it's taking a longer period of time for the reaction to happen to get those hydrogen bubbles forming on the metal, or to get the carbon dioxide forming, where we see this pH sitting really close to neutral, what's happening is that we're getting fewer hydronium ions that are being released, and so a weak acid reacts incompletely. Less than 50% of it with water will form hydronium ions. So an example for this one is, let's look at the acetic acid. Remember, acetic acid is something that we find in vinegar. We're going to react it with water. This is going to become the proton donor. And this will be the proton. I'm just going to write P plus for proton acceptor. So we get the H3O plus, indicating that it's an acid, and CH3COO negative. But this reaction, less than, I wish I had a marker that would work. Less than of this reaction, RXN stands for reaction, will go to completion. What that means is that this is going to go from acetic acid to acetate to acetic acid to acetate to acetic acid to acetate to acetate. It's going to go back and forth and back and forth. Only less than 50% will go to acetate and stay as acetate. Weak acids, remember I told you, is found in our food system. Lactic acid is a common product within a milk product. It's also part of the Krebs cycle when we're exercising and we get muscle cramps. It's the buildup of lactic acid in our body. Here we have stearic acid that we find in animal fat. Citrus acid that we find in fruits, so limes, lemons, oranges. Tannic acids in tea and coffee, they're called tannins. These are what I'm allergic to. I can't drink tea. And carbonic acid in drinks. So carbonic acid, H2CO3 aqueous, is what we find in Pepsi and Coke and root beer. And carbonic acid is actually in all of the bubblies. What I'm thinking of is the dark coloring in there. So let's pause it here and go and work on properties of strong and weak acids. So you're going to go and work through the lesson number 2, properties of acid, property of strong and weak acids, and you're going to look at monoprotic acid. Mono meaning that there's one, okay, one hydrogen or one product that's being, one reaction. I'm going to write that, one reaction happening. And the reason I say monoprotic is because we're going to go and talk about polyprotic acids and what that looks like. So pause it here, work on these questions, and then come back and work on your notes. Okay, strong and weak bases. Having a high electrical conductivity, so before we were just calling it conductivity, it's the same thing. The acronym for electrical conductivity is EC. A fast reaction rate and a very high pH 7, so definitely greater than 9. Greater than 9 up to 14. These are what we're going to call strong bases. Okay, the reverse, having a low electrical conductivity, especially if it's a molecular base, a slower reaction rate, and a pH that's lower than this 9 but still greater than 7, we're going to call these weak bases. And so how do we explain the difference between the two? Same concept as talking about a strong and weak acid. Strong bases will dissociate completely. Sodium hydroxide. when we put it into water, it will go straight to sodium ion and a hydroxide ion. I really do apologize for this being dark. So strong bases will completely break down into its ionic components. A weak base, though, of either ionic or molecular. Okay, a strong base is all ionic, but a weak base can be ionic or molecular that reacts partially with water. So this would be a weak base. And the common one for this is ammonia. Ammonia is what we put in our window washing fluid. When we react it with water, what happens is this becomes the proton acceptor. This becomes the proton donor. We're going to get the ammonium ion, and we're going to get the hydroxide ion. This being the piece that tells us that it's basic. It won't stay there though. It'll go between the ammonium ion and ammonia. It'll go between the hydroxide ion and water. It will go back and forth because less than 50% of this reaction goes to completion. So where it goes and it stays the ammonium ion, where it goes and it stays the hydroxide ion. And really, if we were going to write a true reaction, we would say NH3, aqueous, and water are going to give us NH4, OH. That's a true chemical reaction where we don't have any ions, but we have completed compounds. Okay? Explain the weak base properties of baking soda. Well, you have to know what the empirical formula is for baking soda. I'm going to tell you that it's sodium bicarbonate. You can look it up in your periodic table if you don't know the words. You look here and we see hydrogen carbon. Oh, of course, it does the very term, but this is also known as bicarbonate. Okay, bicarbonate. Sodium bicarbonate or sodium hydrogen carbonate. That's the technical terms for it. First things first, we're going to have the dissociation, the simple dissociation. So we're going to get our sodium ion and we're going to get our hydrogen carbonate ion. And then we're going to look at this hydrogen carbonate. So we're going to take hydrogen carbonate. We're going to react it with water. And then less than 50% of this reaction is going to happen. This is going to be the proton acceptor. We're going to get H2CO3, and we're going to be left behind with hydroxide ion. So why does sodium acetate have a pH of 8 when it's dissolved in water? Because sodium acetate, first of all, is going to do simple dissociation into its ions. Sodium ion and the acetate ion. I'm going to take my acetate ion. I'm going to react it with water. This is my proton acceptor. This is my proton donor. And I'm going to get acetic acid and a hydroxide ion. And when we go back to that really fancy page that I showed you, page 8 to 9, here is either acetic acid or the acetate ion in the top 6. Nope, not even close. We go and we look way down here to acetic acid. Right here, acetic acid, CH3COOH, CH3COO negative, acid base, below the magical hydronium line. Therefore, these are all weak bases and weak acids, and these 6 up, are a strong acid and a strong base. So, we've explained weak base properties of acids and bases. We've explained strong base properties and strong acid properties. Now we're going to finish this off. We're going to go back to lesson 2. We're going to look at strong and weak acid properties, and we're going to do only the monoprotic ones, numbers 1 through 4. And this summary table right here, the empirical properties and the modified Arrhenius theories, you need to understand this. You need to understand empirical properties are things that we see, touch, taste, hear, smell, and the modified Arrhenius theory is exactly that. It's a theory. Okay, where we see low conductivity here, we're talking about molecular when we're looking under bases. Molecular being NH3. Okay, that's the most common example. All right, work on these questions and then we'll flip on over to the next lesson.